All right, so what does 10.8 number 6 say?
Oh, it just says observed values, college classification, spring break destination. Instructions were cut off on the online, so I don't actually know what it's going to do. That's why I'm asking about it.
Ah, sorry.
That's okay. It has a table, but the directions were you observe the contingency table to find the expected value, contingency table for each following.
Okay, so find, basically it just says find the expected value table. So what kind of a table is it?
It's speed, or it's like classes of like grades, like freshman, sophomore, junior, senior, total.
Are those the columns?
And then, well, no, those are the rows.
Those are the rows?
And then, so it's where people go for spring break.
Ah, okay. So it's freshman, sophomore, junior, senior,
Yep.
and this is where they go for spring break.
Beach,
Beach,
mountains,
mountains,
city,
city,
home,
home.
and total.
Okay. And what were the numbers?
What do you want to go across?
Sure.
19, 2, 7, 24. You just start with 1.
Yes.
Yeah, 24 and 15, 4, 3, 20,
52 up here.
42,
2.
18, 1, 9, 19, 47, 21, 6, 4, 20, 51, 73, 13, 23, 83, 192.
Alright. So, .8 number 6. I assume this is just find the expected values.
Yeah.
Yep. Yeah. Alright, so. So note the expected value table will have the exact same format, right? So what was it again? Beach, mountain, city, home. And freshman, sophomore, junior, senior, right? Alright. Now, how do I fill these boxes in, folks?
You take sorry. You take the total number
Mm-hmm.
with that column's total number,
Mm-hmm.
and you divide it by the total of columns and rows.
Mm-hmm. So 52 times 73 divided by 192. Total in the column, the total in the row, the total divided by the total. Less. And then rinse and repeat for every cell in the block, right? So 52 times 13 all over 192. And then 52 times 23 over 192. 52 times 83 all over 192. Rinse and repeat now with 42, right? 42 times 73 over 192. 42 times 73 over 192. 42 times, oops, not 73, 13. 23 over 192. 42 times 83 over 192. So that one number is what's going to change every time. Now it's going to switch to 47, but all the other numbers stay the same, right? So 47 times 73 over 192. 47 times 13 over 192. Etc., etc. 23 over 192. 47 times 83 over 192. And then last but not least, 51. 51 times 73 over 192. 51, 13, 192. 51, 23, 192. 51, 83, 192. And then it just becomes a matter of crank, 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 to do crank, 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 crank. Can you pop the calculator in for all of those and get some numbers? $19.8, 3.5, 6.2, 15.8, oops, 22.5, sorry. Right numbers. 16.0, 2.8, 5, technically 0.0, 18.2, 17.9, 8.2, 5.6, 20.3, 19.4, 5, 6.1, 22.1. At least those are what I got. Assuming I didn't screw up punching the calculator. And this is all you needed to do for this problem, was to create this table. Basically just looking for the numbers in blue. In theory, if you had to take it the next step, then you would do the whole subtract, square, add, right? Subtract, square, divide by, the expected value, add. That gives you your chi-squared statistic. Compare that to the chi-squared critical statistic. If you're greater than, you get to reject, etc. And remember that doing this test, folks, right, this is the test for independence. Or the test for association is what it's also called, depending on who you're listening to is talking about what kind of test this is. And again, the idea is whether you're trying to see whether or not some of these things are related, right? If there is a difference. Does it make a difference if you're a freshman, where you're going to go? If you're a junior, where you're going to go, etc. Those sorts of things. Any others from that section that mildly problematic? Confidence levels? Come on, those are the best. Not bad? Alright. So, get to work on those. Again, if you can get it done this week, that'd be great. Don't sweat it too terribly much, though. I haven't given you back any homework for a few weeks, so I'm as equally to blame as you guys are, so take your time. Eventually, I'm going to get caught up, I swear. I do plan to be out of Monroe on Monday next week, so the plan is by Monday of next week to have all the homeworks graded that you've given me up through hopefully the midpoint of chapter 10, and so I can get them all back to you. That's, knock on wood or simulated wood. Hopefully that will happen. All right?
Did you get my email with my homework attached to it?
Yes, I did, Heidi. Thanks.
Okay.
Did you still turn the hard copy in down there?
No, do you want me to?
Would you? I mean, some of the lines were a little faint, so it's probably just safer if you do, just to be safe.
Okay.
Thanks. All right. So. So, back in chapter 8, we learned about calculating confidence intervals for means about just one sample. And then when we went into chapter 9, we said, oh, we can also calculate confidence intervals for the difference between means, right? So we could actually take two independent samples and say, hey, let's compare these two and see what the difference of the mean between one independent group and another independent group is. And when we moved into chapter 10, we basically said, hey, let's do hypothesis testing, but let's do hypothesis testing with just one population, only caring about one population, very similar to chapter 8. So if you think about the progression, chapter 8 and 10 are very similar. Chapter 9 and 11 should be very similar. So guess what chapter 11 is going to do? Still going to be hypothesis testing, but now instead of hypothesis testing on one population, we are now going to be comparing two independent populations. And again, independent is in quotes because we're going to deal with one case where the two populations can be dependent. And if you remember, that's where we talked about before and after testing. That's going to be here in chapter 11. Except now all we're going to be doing on this, folks, instead of doing confidence intervals, we're going to be doing hypothesis testing. So, think about back to chapter 9, when we were doing confidence intervals. What types of confidence intervals did we do first with two populations? We tried to compare two populations that had large sample sizes, all right? So 11.1, compare population means with large sample sizes. And note again, large in statistical sampling basically means that the sample sizes are going to be more than 30, both of them, right? And again, remember there's two populations, so one is the first population, two for the second population, right? Now, when we were back in chapter 9 doing confidence intervals, we would figure out a confidence interval for the difference between means. We're going to carry on a similar sample, or a similar style, right? Back in in chapter 9, we look at x bar 1 minus x bar 2 plus or minus e, right? So we're going to do something similar, except now we want to be doing it with hypothesis testing, okay? Instead of doing a plus and a minus, now folks, we are actually going to be doing a comparison, right? So we're going to say something like mu1 minus mu2 is going to be more or less or not equal to. Well, we're going to start with something along the lines of 0. Why do you think I wrote each one of those up there? They're all going to be slightly different, but these ones are going to be one-tenth. So when we're doing greater than or less than, these are going to be one-tail tests. So you're only going to be checking whether or not your statistics are greater than if you're doing greater than, or less than if you're doing less than. Okay, so same sort of stuff we were working with in the last chapter continues to carry over. And of course, if we're doing not equals to, then it's two-tailed. You can be greater than the alpha over 2 or less than the alpha over 2, right? So whenever it's two-tailed, you gotta split your alpha to both sides, right? Now, I'm using 0 here in this example, folks, just because it makes the numbers easier. Note that this number could be any value, okay? This number could be 5 or 6 or 1 or 2, or it could be a negative value like -3 or something along those lines. And the idea is that, you may want to try and show that one population's mean is more than 3 points larger than the other population's mean, okay? And that's when this number will be something other than 0, okay? Right now we're just doing 0 because it just makes the numbers easier. And note, this difference, which is why I write it up here because it's very similar to what we did back in chapter 9, but really what this turns into and so what we're really testing when we're testing mu1 minus mu2 is greater than 0 is testing that the population mean of the first population is really greater than the second population. And if you want to do it in the reverse order, that's where you go the other direction. And then if you're just trying to prove that the population means are different or equal, that's when you're doing the last one, right? So the testing is all going to be based off of the difference. We're going to be doing subtraction, but realize what we're really testing is whether or not one population is more, less, or not equal to the other population's mean, okay? And that is a very standard test that you want to take, is to say, hey, let's look at a population of, men over 70 versus women over 70. Which one of them has, which of them has a higher, blood pressure testing on average, right? And based on that, when you do blood pressure tests, you should be spending more time checking men as opposed to women if the population of men has, in general, higher blood pressure ratings, right? this is the sort of stuff that statistically is done in the hospital setting all over the place as to determine how picky they are at running specific tests. They will put you into a specific population and say, is your population one that has the most likelihood of a certain type of disease or type of difficulty? And so they'll test you for those first. And if they can then disregard those as not being the problem you're having, that's when they start getting into others, right? But again, the idea here is to limit the number of tests you have to perform on someone, because every one of those costs money, right? And if we can reduce the cost of care in general, then the cost of care for everyone actually starts to go down. So it would be really nice if hospitals would start gathering this data and actually analyzing it better so that they can start trying to pinpoint what tests to run on what individuals when they come in for the hospital with certain conditions. Again, they're getting better at this, but this is the sort of thing where they have to get as good as possible, because that's what's going to start reducing costs, period. All right? There's actually a study that my brother has been doing with the University of Wisconsin Medical Center right now. He's actually testing to see, hey, if you know that a certain population has a higher risk of having alcohol-related incidents, should we be having interventions with that specific population on a more regular basis anytime they show up in the hospital? And he's trying to see if that actually makes a significant difference in cost of care for that particular individual. How much does the hospital spend taking care of this patient if they don't talk to them about it, do talk to them about it? And if they can prove that by doing interventions at any given time for a specific population, regardless of whether they actually have a specific problem or a specific accident, if you do the intervention, will it potentially lower costs? And if it does, then you want to just sort of recommend this to every hospital that they all should do it, no matter what. When a male between the age of 18 and 25 comes into the hospital, should you have a talk with them about alcohol-related accidents? What do you guys think? I mean, again, it's one of those where, but if the numbers bear out, if you can prove using statistical data that it actually makes a difference, then you can start trying to say, okay, Medicare is actually going to pay for a doctor to do this. And then it'll start happening everywhere, okay, that kind of a business, all right? So this is actually something that is relatively commonly done out there in the real world, comparing two populations to see which one is having a higher mean for whatever it is that you're trying to measure. All right, so, okay, so note, our tests will all be based on mu1 minus mu2, but our hypothesis test can boil down to mu1 less than greater than equal to mu2, okay? So again, the idea here is that we're really trying to compare two populations as to whether one has a higher mean than the other. But the method that you do it with is by doing the difference comparison, okay? All right, so okay, so because the sample size is large, what statistic am I going to use? When the sample size is small, we always have to use T. When the sample size is large, we always get to use Z. And again, this should look very similar. Basically, that's very similar to what we did to calculate our error value back in chapter 9. The only difference is we weren't taking a sample, subtracting a specific test that we're trying to do. The only difference is adding in the testing. And just like we've been doing in chapter 10 for the longest time, you're going to compare this to the z-critical value, whether or not to reject or not reject the null hypothesis. And the same sorts of things apply, right? If we're doing a greater than test, your z-statistic must be greater than your z-crit. If we're doing a less than test, your z-statistic must be less than the negative z-crit, etc., 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 okay? All right, so let's see. What should we study? Okay, so just a classic example to go off of, right? So suppose I want to test if women are better at math than men. So, I take 50 men from my math classes, and they have a mean GPA of 2.75 with a standard deviation of whatever, let's say of 0.8. I take, say, let's go the other direction. Take 60 women. And let's suppose they have, with a GPA, a mean GPA, of 2.82 and a standard deviation of 0.6. And let's test this. Test at alpha equals 0.05. Okay. So here we go. We're trying to do the classic Battle of the Sexes test, folks. So, since this is hypothesis testing, ho and ha. So now, before you jump into this, folks, you got to define your populations first, okay? You got to define which is your first population and which is your second population. Okay, so X bar 1 is 2.82. S1 is 0.6, and N1 is, how many women did I pick again? 60? Okay, 60. I just made the women first for whatever reason. So what is X bar 2 then? 0.75, S2 was 0.8, and N2 was 50. So, first population is women. Second population is men. So, what am I trying to show, folks? How do I write that mathematically for my hypothesis testing? Again, determine what I'm trying to do. Are you testing something or are you wanting to show something?
You want to test that women are better. So that's the testing part.
So that's going to be the ha then, all right? So what do I want to be true?
That women are better.
That women are better. So what am I going to say mathematically using ones and twos?
So that would be your X1.
Except use mu's because now we're at the population level. Yeah, you're on the right track.
Okay, so
Your mu1
minus your mu2
minus your mu2
is
greater than or greater than, let's go just straight up better, so let's call it greater than. That's right. Why is that correct?
well, your women is the first group, and you want that one to be better than the other one.
Exactly. Essentially you want mu1 greater than mu2, right? To say that women have a higher math GPA than men GPA. And so normally it would be mu1 greater than mu2, but remember our hypothesis testing always does subtraction. So subtract the mu's to both the same side. So what's my ho if that's my ha?
So M1 minus M2 is less than.
All right, so now, what's my z statistic? What am I going to calculate?
We just do from X1 minus 3, so 2.82 minus 2.75 minus
What's the comparison of my mu's?
0.
Yeah. So whatever the subtraction of your mu's is, folks, that's what you're going to use for mu1 minus mu2. Since all I'm trying to show is that they're greater than or each other, greater than or less than or equal to each other, straight up 0. So the difference between the two of them that we're looking for is 0. Now what am I going to divide by?
0.6 divided by 16.
Careful, right? So remember it's the square root of all that stuff squared, right? 0.6 squared over 60 plus 0.8 squared over 50. Now remember, you're adding those, taking the square root of them, and having them all in the denominator. Yeah. Fun calculator. Punching, right? 2.82 minus 2.75 divided by the square root of 0.6 squared divided by 60 plus 0.8 squared divided by 50, close the parentheses. Now remember, folks, this is a z statistic, so you can go either way you want about testing this. You can either look up the z critical value and determine if this value is greater than your z critical value, then you can reject. Or you can look at the p statistic or the p value of this z statistic and say if my p value is less than my alpha, then I can reject. All right? So either way you want to do it, right? So either z stat is greater than z critical to reject, or p value is less than alpha to reject. Either of those will do exactly the same thing. So-
finding that C stat versus your Z crit, how would you look that up? Do you use the N for each one of them?
Well, remember z doesn't work with n.
No, you have to find the D.
Nope, that's only a t. That's only with t. With z statistics, you get to use table A or B, right? In fact, you should use table B with the critical values along the bottom, right? Remember that the critical values down below, folks, are all two-tailed, okay? So on table B, if you look at the bottom, those are all two-tailed. Note what kind of a test we're doing. One-tailed, right? Because we're doing greater than or less than. Two tails are for not equal to. So we want to have that region be 0.05, right? And note that the table is splitting it up into two sides. So don't look up the level of confidence at 0.95. Instead, look it up at 0.90. Just get this.
So it's because you had a standard, you had an alpha.
Because I had alpha at 0.05, right? Again, note the other way you can go about doing this is just looking up the p-value. So if you look up z 0.51, 0.51, and remember to always look it up negative. So our z statistic is 0.51 greater than 1.645? Obviously not. And is 0.3050 less than 0.05? Obviously not. So therefore, we fail to reject the null hypothesis. And sorry, ladies. According to my data, you can't say that you get better math grades than the men, at least according to this study that I did.
Can you scroll back up to the condition?
Which one?
No, yeah, the first one. I clicked something wrong. 3 different times and keep getting 0.07.
I do the math in smaller portions, so like I minus the thing first, did the square or the bottom part first, and then put them together.
When you subtract the two on the top, you get 0.07, I agree. Right?
Why isn't that in the rest?
And then divide by parentheses, 0.6 squared divided by 60 plus 0.8 squared divided by 50. Close those parentheses. Oh, did you get 3.6 .72.
No, I got 0.07.
You guys getting different numbers than I got?
0.8
I did originally when I tried to do it all together.
2 point
I got 0.6 something.
I got this.
Did you get the .51?
Yeah.
Monroe folks, did you get .51? For the Z statistic?
I asked if I got it.
Oh, there I go. Okay. I was smoking crack for a second. What did I do? Oh, I didn't take a square root. Oh, never mind. Look up negative .51 in the Z table.
Oh, right, okay.
Did you get it, Kyle?
Got the same 0.07, so probably the same.
Alright, so do the .07.
0.07.
Divided by parentheses, 0.6
I'm pretty sure it was.
squared. Oh yeah, don't forget the square root. Just 6 squared divided by 16 plus 8 squared divided by 50 parentheses. Now I messed up. Always, as soon as I watch, it works.
How did we get 1.6?
So when you go to the critical table in table B, absolute front of the book.
Oh, okay.
So table B, the bottom.
Mhm.
So you know how normally if you were doing a two-tailed test, you would look at 0.95.
Mhm.
Okay? But since this is one tail, you have to double your alpha. And so what's 2 times 0.05? That's 0.1. So that's why we looked up our critical value under 0.9.
Oh.
So when it's one tail, double your alpha to switch it to a two-tail lookup.
Okay.
All right?
Yeah.
So was it 0.51 or?
If you got to look up negative 0.51 in the table A. Good? All right, so what did I assign from that section? How mean was I?
8, 12, 16, and 20.
Oh, that's not too bad. All right, so let's see. Which one should we do? Oh, an 8's not even a. Just write the. Okay, so. All right, so let's do number 10. Talking about salaries and degrees, okay? All right, so master's degree versus bachelor's degree. All right, so let's just write the data down really fast. So X bar 1 is 38,400. S1 is 100. And I sampled 42 people. Bachelor's degree, X bar 1 is 36,750. 2. S2, 3,700. N2, 45. And And the claim is that you make more money if you have a master's degree than if you have a bachelor's degree. Claim, test, if master's earns more than a bachelor's. So what do we want to have true? We basically want to have the master's degree be more than the bachelor's degree. We want to believe that mu1 is greater than mu2. And this tends to be how I write it. I write it like it's a test of comparing the two populations at the beginning and then convert it into a subtraction. If you can do the subtraction in one step, that's fine. I have no problem with that. But I do this just so that I can kind of see what I'm doing first and then convert it into what do I have to test second. All right? So this is just me showing more than I necessarily need to, but you don't have to if you don't want to. You definitely need the second part of these though. So the official right test are these two things, okay?
So for the hoe, it's gonna have that equal to sign on the bottom, right? Most of the time.
Most of the time. Again, it kind of depends on what you're trying to prove and how they word the question too. Because they could say, something along the lines of, we don't think that a master's degree makes you more money, and we want to prove that it really doesn't, and so you sort of have to negate everything and switch it backwards. Hopefully there aren't that many length. Alright, so how are we going to go about doing this one, folks? Oh, and yeah, we had alpha equals 0.05. Note, first off, one-tailed test, okay? So adjust according to the one-tailed test. Now, how are we going to calculate our z statistic? $38,400 minus 36,750. That's the difference in our x bars. Technically, the difference in our means is 0. Divide by your 3,100 squared over 42 plus 3,700 squared all over 45. .26. All right. What's the p-value for that? 0.119. What's our alpha? Our alpha was 0.05. 0.05. Is 0.0119 less than 0.05? Yes. Therefore, reject. And again, you could have used the same z-critical value, since this was the same level of confidence or the same level of significance. Our z-critical was 1.645. Our z-score of 2.26 is greater than 1.645. We would be able to reject using that analysis just the same. All right?
You said because our what was higher?
If you looked up the z-critical value, so the z-critical value was the 1.645. Our z statistic, 2.26, is more than that. That's another way to say you can reject. So the two ways you can test are either use the p-values or compare the z and the z-critical. Or because 2.26 is greater than 2.645. This, of course, will be z-critical. Normally, folks, though, in general, when you're working with the z statistic, you should play around with the p-value. You should really get in the habit of using that to do your comparisons, just because that's what's commonly used out there in the real world right now, anyways. At least every paper that I've seen in the last 5 years has gone to p-values only. I was even helping one of my coworkers finish her PhD thesis. She was writing some statistical study, and her data was all based off of p-values in the end as well. So I was like, okay, it's pretty standard. Alright, not bad. Again, please remember though, if you're doing a two-tailed test, remember to double your p-value when you look it up. Right? Two tails always doubles the p. Alright, not bad. So, if we did large samples, guess what? Yeah, uh-huh. Note again, as long as one of the sample sizes is less than 30, you are considered small. All right? Doesn't matter if the sum of them is more than 60 or anything like that whatsoever. If you sampled less than 30 in either of your populations, you must use t-statistics, okay? That's all there is to it. And if you remember back into chapter 9, folks, remember when we had small sample sizes, we had a fun formula and a not so fun formula? Guess what? They're back. Yeah. It's even more fun now. So, if you remember, we had pooled and non-pooled data, or pooled and non-pooled samples, spaces, right? Population variances are equal over here. Population calculation, variances are not. Variance, if I can spell the stupid word. So pooled, they're equal. Non-pooled, they're different. And remember that pooled is the unfun one. So here you're going to do, and everything is going to look really similar. Numerator exactly the same as a large sample size, and then you've just got this god-awful formula that we were working with before, right? N1 minus 1 times S1 squared, all O plus N2 minus 1 times S2 squared, all over N1 plus N2 minus 2. Remember that wonderful formula? It's back, sorry. And it's also got its tag along that comes with it too. When they're pooled, you get to use the higher degrees of freedom, which is why you want this piece of data to work with. And then when you're non-pooled, the calculations are much better, right? X bar 1 minus X bar 2 all over mu1 minus mu2. And now it's just the straightforward formula we had before. S1 squared over N1 plus S2 squared over N2. It's exactly the same as the large sample size. And then again, remember that degrees of freedom. Pick the smaller of whichever one of your ends is. Pick the smaller of your ends, and don't forget to subtract 1 from it, right? So it's an ugly formula, you just got to be able to play with it.
Is that's a T-stat, right?
Yeah, it's the fuzzy t-stat. It's the same t-statistic.
I thought you were doing like the fish that are the alpha 1 or alpha divided by 2 thing over there. And like, what is that?
Nope, no, it's just to it. This is just what you're going to compare to your t-critical value. And again, you look up the t-critical value in the t-table, and it works exactly the same way it did before. If it's one tail, you do one tail on the alpha lookup. If it's 2 tails, look at the 2-tail alpha lookup on the table, right? I mean, just same stuff, right? If it's greater than and less than, it's 1 tail. If it's equal to, not equal to, it's 2 tails. Boom. The cool part about it is all of that sort of keeps continuing to carry forward when it comes to comparison. All right? I am not even going to try and make up anything here. I'm just going to do a couple of problems and then we can call it a day because I'm tired.
11.2, 6, 8, 10, 14.
6, 8, 10, 14. All right, so let's see if we can find one that's got a pooled set of data to start with. Which ones are pooled? All right, how about let's do number 9. We can test Gary's new painting tool.
Damn it, Gary.
We don't want to know what Gary's special painting tool is. It's none of our business, but.
I think his entertainment is watching paint dry.
All right. So, job without tool, job with and job without tool. So without the tool, apparently I'm calling that X bar 2. We should probably call it X bar 1 since the data is giving it to us first. It'll just be easier. Alright. X bar 1 is 4.2. S1 is half. N1 is 6. Gary doesn't work very much apparently.
Freelance.
After he purchased the tool, he looks and sees 3.9. S2 is 0.7. And his N2 is all of 4 jobs. And we wanted to look at alpha equals 0.10. Gary says that without the tool, his average time for painting was greater than with the tool. So he wants to show that without the tool, mu1 is greater than with the tool. mu2. And remember that this translates into mu1 minus mu2 is greater than 0. And the opposites of those translates into mu1 minus mu2 is less than 0. Those are hos and ha's. And this one had variances are equal. So we have to use the crappy formula, or the better formula, in theory. Alright, so. X bar 1 minus X bar 2. 4.2 minus 3.9. The difference between my mu's is 0 because of my ho and ha. And now the joy and fun of dealing with lovely square roots. So, that's 1 squared times that, right? 6 minus 1 times 0.5 squared plus 4 minus 1 times 0.7 squared all over 4 plus 6 minus 2. And then don't forget square root of 1/4 plus 1/6. That's just ugly looking at it.
Let me do the opposite. Just say.
Which one?
Because you technically did yours flip flop, so your 2's are your 1's the way you set it up.
Yeah, I mean, the nice part about it is that
Yeah, and then on that side it doesn't matter. I just said.
as long as these things are together, then it's okay. Just when you're adding underneath the square root symbol, it's all right. All right, so let's see how we do. Ugliness personified. you guys, you can do 4 plus 6 minus 2 in your head. 4 and 6 is 10, minus 2 is 8. Don't put that in your calculator. Divided by 8. And divide that by the square root of 1/4 plus 1/6. You guys get 0.797?
Still working.
Point what?
I left my calculator.
I always got spares up here, you know. You can use your phone though, too, that's perfectly fine. If it's easier on the phone, then
It wasn't.
I would tend to think it's not.
Yep.
Most phones calculators are they're pop, push, so that when you hit the square root button, it immediately calculates it on you, yeah. It's annoying. Well, nice part about it is these things you can do, right? I mean,
I got those.
5 times 0.5 squared is just 1.25, right?
What?
5 times 0.5 squared is just 1.25. This is 1.25.
Yeah.
3 times 0.7 squared is 1.47, right? So this up here is really 2.72. This down here is really 8. It should be just 0.3 divided by the square root, 2.72 divided by 8. Close that, and it equals, and then divide again by the square root of 1 divided by 4 plus 1 divided by 6.
Why would you divide? That's a multiplication.
No, it's still underneath the division symbol. This is underneath.
I know, but wouldn't you just times that to that?
Think about this. What's 8 over 4 times 2? Exactly. If you do 8 divided by 4, that's 2, and then times 2, that's 4. So that's why you have to
So
do
you
8
said that
divided by
you-
4 divided by 2. So here you will do 0.3 divided by the square root of this crap, and then divided by the square root of the other crap. Because division is dividing both of those.
So you have to take, this isn't multiplying that times that, right?
If you do this multiplication, then it has to be all in parentheses before you do it. Or you can just divide them both one at a time. And that's just, it's the same application as this thing. This should be 1, not 4, so be careful with that.
So you're saying take that first section first and then divide it by the section.
So if you do 0.3 divided by the square root of this stuff,
Right.
and get an answer, you can just hit equals. Then if you say divided by, again, this, you'll get the correct answer. Because then you're actually dividing by both of those things instead of trying to multiply by one of them, which is bad. All right, so. What's my T critical value, folks? First off, what are my degrees of freedom? Eight. Alpha's at the 0.1 level. 1 tail because we're doing greater than. Is our t statistic greater than our t critical value?
Our T crit is greater than our T.
Is our t statistic has to be greater than our crit to reject? No. Therefore, fail. We fail to reject null hypothesis. There is no rejecting the hoe here, folks. And we must laugh, ha 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 ha, all the way to end.
That was a pool, right?
Yep.
For the first unit, or the point one,
Mm-hmm.
we don't have to deal with point pooled or unpooled, right?
Nope, there's no pooled or unpooled in 10.1. If you're in the z statistic area, it's z statistic all the time. Alright, so which one of these is not pooled? 10 is, but that's when you're doing, right?
Different than 13.
They diff it in 13. Alright, 13 is the same as the one we just did, though, because we're testing more than. Do we have a less than one? La la la. To see if the bags in line A actually have a weight lower than those in line B. Ah, there we go. Alright, let's do number 11. Those are different, right? Yeah, assume the variances are different. Alright. A and B, X bar, S, and N. Oops, I did it the other way around. I said N, X bar, and S, whatever. 20, 15, 9.6, 11.8, 15.9, 13.2. And so this chip manufacturer is trying to determine if the mean weight of A is less than the mean weight of B, right? Alpha.
We have standard on this one.
Yeah. Variances not equal.
Said one is less than two, right?
Uh-huh. We want mu1 less than mu2, right? So I want to do a left-tailed test at least. So mu1 minus mu2 is less than 0. So the opposite is what the hoe is. So here we're doing a left tail, one tail test. Alright. So now we get to use the easy formula, bad one, the one that's going to give us not as good of a study. So take the difference between your x bars. 309.6 minus 311.8. Again, minus 0. Now we have the square root of S1 squared, 15.9 squared, all over 20, plus 13.2 squared, all over 14. Much easier numbers to deal with. Crank.
At least that one worked.
Hmm?
So at least that one worked.
What are my degrees of freedom, folks?
14.
14. Why 14 then?
Because that's the small one.
The smaller one is 15, and you take one less than the smaller n for your degrees of freedom when you have to use the crappy formula. Or sorry, the easy formula. And again, since it's just less than, it's one tail at the 0.1 level. What was that?
You do one tail, right?
One tail, yeah, that's the top part.
1.3.
And note, because we're doing less than, folks, it's not 1.345, but and we need to be more negative than that. Is our t statistic more negative than this? No, therefore, alright, so not too bad. Again, these are just kind of getting used to this sort of ho and ha concept where you're really comparing two numbers. Note, there will be times when this value is not 0 though, okay? Yeah, it'll say the difference between these is more than 3 or less than 4 or something along those lines. And so you'll basically jump right to this. The difference between these is more than 3 or something like that. Okay, so look for those because that can happen. Basically then, instead of having this minus 0 at the end, you've got whatever that difference is over there. So, alright? Alright, so if you want, starting on 11.1 and 11.2 homework, but that's all I'm giving you for today. We weren't going to get any past this, so that's cool.